Hello everyone, this is my second time recording the electrical workshop, but yeah, let's get right into it. So pretty much we've chosen all the components that we have for our electrical design and a lot of it's shipping. So, if we look back at, one workshop ago, we have the motor that we have bought, everyone has gotten the motor at this point. We have the battery, which we have got, everyone has bought the battery, and some sort of input device. So we already have this as well. So for the skateboard team, this is like some type of remote control of some sort. This is something that you might want to consider making later on. Or, if we already have it, you can just use it. So that's for the skateboard team. For, the bike, you guys have bought a throttle controller. So pretty much you just spin the throttle and it goes forward. So that's for the bike team. And for the skateboard team, you have an IMU or inertial movement unit, right? Which pretty much measures how much you rotate on a gyroscope, in the X, Y, and roll directions, pretty much. And that's for the one wheel, right? So that way it senses which way you're tilting and is able to go forward. You also have the pads that, check if you're standing on your one wheel, if you remember correctly. So that would also be very useful. Anyways, so we have chosen our input device, and our last big thing that we still need to do is do our motor controller, which is kind of the main task that you have as the electrical team. And we're gonna start by making the schematic for it. I know last week we already started making the schematic and everything, but we're just gonna continue on that, right? So just to recap, this is our main high-level block diagram of how our motor controller looks like, right? So we have some input that we're going to get from our input device. So it's either maybe an RF signal or a remote control signal from our skateboard, maybe an analog signal from our bike throttle, or for our one wheel, it's some sort of communication protocol that we have to talk with the MCU. So some type of communication protocol. So either way, we have some input, and then we translate that input into an output for our motor, right? So depending on our input, we're going to spin our motor some amount. So we're going to spin it some amount. Motor spinny, right? Now, we already have figured out the input, which is our input device and our motor, and how we're going to power it all, obviously using our battery, right? Now the only thing that we have left is the middle circuit that we're going to design now, right? So as I said before, we have a microcontroller that's going to take in the input, right, directly, and then produce the signals that we need to actually spin the motor. Now this is going to be translated into our motor driver, right, which will provide transient protection, and is also going to amplify our signals so that they can actually switch on and off our transistors. Amplify signals. Now the good thing about the motor driver is that it's kind of like a black box that does a lot of processing to it. So we just have to read up on what signals to send it and send them that signals, and the motor driver will do a lot of processing for us. All right. Other than that, we have some transistors here that's main purpose is just to turn on and off, right? And we need to do it in a specific pattern to spin this motor pretty much. Now, fortunately for us, we don't need this on and off. We don't need to know the specific pattern for it since that's a lot of the firmware fault, or not fault, or that's the firmware's issue, right? So they're gonna write the complex algorithms that they need to spin these, or to turn on and off these transistors and spin the motor. All right, so what's kind of the design process of making it, right? So I kind of went over the high level block diagram of how the motor controller works, or the so the first thing is research, right? We have to research on what we actually need to make, right? So this is kind of already done for you. Anything that you could ever need to know, you can ask me or reference previous documentation that we made, or a combination of both, or Google, right? Previous info or Google, right? And honestly, that's all the information that we need to know to be able to make one of these motor drivers, right? Now, part of this research is pretty much done for you. So just make sure that you accumulate or gain the knowledge that you pretty much need to know to make one of these at this point, right? So it's more of a learning thing than researching. All right. Afterwards, we need a blueprint to actually make this motor controller, right? And that is in the form of schematics. All right, so you may have seen schematics in stuff in courses like ECE 140 or any other linear circuit courses. Now the difference between schematics that we're doing and the schematics in like EC140, right, is that these are like linear components, and we do a lot of math to be able to, solve these circuits, right? But the difference is for our schematics is we look at the component that we have and we read the data sheet behind it to be able to reproduce pretty much what the specifications that we need to, I don't know, make the motor driver work or something like that, right? So all we have to do is look at the schematic and reproduce it. Now, after we make the schematic, which is kind of like our blueprint, right? We're gonna make a PCB. So we're gonna do PCB design, right? So if the schematic is our blueprint, right? The PCB design is like actually making the thing in real life. So if you imagine a building, right? An architect will draw up a blueprint on how to make a building. An engineer will, make a how to actually make this thing in real life, and then you actually have to build it, right? So the schematic is kind of like the blueprint that we have to follow, and the PCB design is how we're going to make it in real life. So it's placing all the physical components actually on a circuit board, all right? So PCB stands for printed circuit board, right? And printed circuit boards are anywhere where you see electronics, right? You're probably around like at least 10 of these things at a given point, right? Your monitors have them, your keyboards have them, your mouse, your phone, they all have printed circuit boards. And we're going to design our own to pretty much make this motor driver or the motor controller. Afterwards, we're going to have to order our PCB, right? So we use a website called JLC PCB, which manufactures and assembles some of this PCB. So we send over the files on how to make it, right? Or like the actual physical design, and we send it to this website, and they're able to pretty much make the PCB for us. Now afterwards, we have to solder any components that aren't already on there, right? So, if we're missing like a capacitor that we need to solder on, we have to, melt it onto the printed circuit board so that we can have a capacitor on our circuit, right? Now, the last and most important thing is testing, right? So after we solder, we have to test all the components, make sure everything works as expected, maybe put some test firmware and see how the signals look, right? So this can look like a variety of things. The main one is like looking at signals through an oscilloscope. All right, cool. So these are kind of the 6 steps that we have to go through anytime we want to make a motor controller, or anytime you want to make any circuit, really. These are the 6 steps that we're going to go through. Now for research, right, since we're a really beginner at this type of stuff, we're going to reference a really good open source library called VESC, right? And now what the VESC is pretty much, well, as I said, it's an open source library that where someone made a motor controller for us, pretty much, and they made it open source for anyone to use. And it's kind of like a really good industry standard that a lot of people use to move these type of portable electric vehicles, right? So if you look at this link right here, there's already a lot of circuits that are done for us, and you can see the high level block diagram is kind of pretty much what I have before with a few additional things, right? So here we have our microcontroller that's connected to our motor driver, which is the DRV8301, which is connected to our transistors, or he calls it the power, right? So if you just scroll down, right, you can see that a lot of the work is done for us. So instead of actually, making everything from scratch, what we're going to do this term is instead reproduce the schematic from this motor driver, that's already pretty much done for us, and just remaking it in Altium. This way we can like learn essential schematic making skills, right? And but like even though we still like might not know what everything does, we'll still learn how to like put things together and like actually assemble something. And mimicry is like a really good way of learning, just like how coding, you kind of just copy people until you figure out what's happening. Same thing for schematic design. All right, so the first thing that you're going to do is you want to download Altium from the Altium website. So I believe the link is right here, and I also posted it in the electrical chat for you guys to view. But this is the link, altium/education/student licenses, and pretty much what this link leads you to, sorry about that, is to be able to enroll for free for Altium Education. So if you fill out this entire form, they'll send you an email and you can get Altium pretty much for free. So let me pull out Altium really quick. Now, Altium is the industry standard for pretty much any circuit design, right? And a lot of people in the industry use Altium to make whatever circuits that they can. So here's a few examples like iRobot, MKS, and KArcher. And the reason why we're using Altium is really to just get the experience of being able to go from a schematic to a PCB to having it actually in our hands. And it's a really powerful tool that costs a lot of money if you aren't a student. But since we are students, it's completely free for us, which is amazing. All right. But it does take a while to load. So, yeah, just to reiterate, we're gonna remake this schematic, and if you have any questions at any point about, how, like, what things do, like, for example, like, what is this component, for example, feel free to always ask. I feel like that's the best way to learn and kind of immerse yourself in what we're doing. And then we can answer. So if you ask like, what's this component do? I'm like, oh, this is an inductor and it's used in a buck converter, and that's what this part of the circuit does, right? And that goes for any part of the circuit. Now, of course, if you need any help, you can also just Google a lot of the time, which is a really, really useful skill. So if I Google DRV8301, look how many times I pressed this already, and I look at the data sheet for it, I can learn a lot of information from the data sheet. Yes, it's boring. That's why I kind of recommend maybe asking us first, and then we've read through the data sheet like hundreds of times. Okay, maybe not hundreds, but like quite a few times. So like if you need help with anything, you can always ask us. All right, so Altium has loaded for me. And pretty much this is where you're going to be making your schematic, right? And I think a lot of you have already started on making your schematic, which is really, really great. But what your job is to pretty much figure out as an electrical team how you're going to split up all the work, right? So obviously, like from what I've shown you on the schematic on the VESC, right? It kind of seems like a lot, right? And we're gonna be referencing this VESC 6.4, by the way. But it seems like a lot of work. But if you break it down to, you have like 5, 4, 6 people in your teams, right? If you break it down in six parts, right? It's actually not that bad, right? One of these schematics might take 2 hours, right? But split among 6 people, now it takes 2 times 6 is 12 hours in total, but 2 hours each person, and then you can get everything done. So I really recommend communicating a lot with your team and being able to split up the work. So if you notice, these are like separate schematics, right? So this is one schematic, this is one schematic. And in the end, they link it all back in this high-level sheet diagram or high-level block diagram. So kind of what I recommend is, first you make this high-level block diagram, and then people can work inside each individual schematic. So if you see, this is the MCU schematic, and if we scroll down, this is the MCU schematic. So this schematic is linked to this high-level hierarchical sheet, right? And each one of these designators, so for example, voltage 1, is linked to the voltage 1 designator right here, for example, right? So what you're going to do as a team is, maybe one person takes the MCU, they make this entire schematic, all right? One person takes on the motor driver, they make this entire schematic, all right? And then at the end, you can link it all together in the high-level block diagram. That way we avoid a lot of conflicts that might occur, and people work in kind of their individual sheets in order to avoid like a lot of conflicts that might occur. All right, cool. So let me show you around Altium. So I think you would already, for the bike and skateboard, you already have your projects up. For one wheel, you're using KiCads, and I already kind of went over that for a few, so that's kind of an individual thing. But if you notice here, right, the skateboard already has a lot of the high-level block diagrams, and you're pretty much just following exactly what they do right here, right? So here we have a lot more sheet files that, for example, this has the NRF sheet tag that would be corresponding to NRF here. But this servo sheet tag would correspond to the servo one, for example. And if you go into, I guess, the left bar right here, you can see that you can go into each individual sheet and be able to edit it. So what you're going to want to do is coordinate with your team, who's going to take this. And you can make a new sheet by right-clicking on this and creating a new schematic, and then working on each schematic on your own, pretty much. And then at the end, you combine all the sheets together, and it's very nice, right? So I already did the liberty of making one of these and pretty much like copying one of these schematics. This project is called the EESCV. EESCV 3.0. right? And you can pretty much open this project by pressing this button right here beside electromobility and pressing open project. And then you can see all the projects that we have ongoing at Electrum. So another really important thing that I forgot to mention is you have to check your email to make sure you have the invite to Altium, right? If you don't have an invite, make sure to reach out to me so I can invite you, right? And you can join the workspace by just pressing on the email, accepting it, and it should just pop up right here in the top right corner. And that way you can start opening all your schematics. So if you need any help, referencing a schematic, you can reference mine that I have right here that me and Winston made, right? And we kind of did all the importing work because we don't really know how Altium works too. So this is kind of like our learning curve. But we really want you to individually make it and learn how schematic design works, right? And each individual design will be very different, right? And that's kind of the point. We want a variety. So just a few tips, right? When you want to modify anything on your schematic, everything is on this top bar, right? And if you hover over it, it tells you what things do. So place a wire, for example. If I press this, I can place a wire and connect 2 points, right? I don't want to actually edit it, my bad. But yeah, you can do that. If you want to place a part, you can press place a part, and it shows up this dialog menu on the right side that pretty much shows all the components that you want. So what I recommend is having a few panels open. So you don't want to use this main components panel. You probably want to press panels right here and use the manufactured part search. And this pretty much lets you choose a specific part that you want to use. And what's really great about this is that not only does it give you the schematic symbol, but also links the corresponding footprint. All right, and what a footprint is pretty much what a schematic or what a symbol would look like in real life. So for example, if I just look at capacitors here, or here I can look at this resistor, right? It might have the schematic symbol of a resistor right here, but it also has the actual footprint, like 3D model of how it would look in real life, and it will place it automatically for you. So I would recommend using these components opposed to the actual components right here. And this one is also linked to the internet, so it has things like price. So this one is, well, if it doesn't want to disappear, this one's 0.0066 cents, or yeah, so which is really good, or $0.0066. Anyways, you can simply drag and drop and place down your component, right? This is going to break a lot of things for me because it doesn't want to update, and I shouldn't update it, but you can do it yourself and work with your team to figure it out. That's pretty much all I want to say. So again, what you're going to do, and the main thing you're going to do, is look at the schematic, split up the work in individual sheets with your group members, go into Altium, start making it. If you're on Onewheel, do the same thing but in KiCad. All right, communicate with your team and let's get this done. If you have any questions, again, feel free to always reach out to me, and I'm down to just go one-on-one. We can finish it together if you want. But it is a really important schematic that we want to get done as soon as possible, hopefully before midterms, so that we can wait for shipping times while we're studying. And if we get this, then we can test it afterwards, and we'll have a really cool motor controller. All right, that's pretty much it. Thanks to everyone.